Okay, so today we're going to be looking at haloalkanes for A-level chemistry. So haloalkanes contain carbon-halogen bonds, and these bonds are polar, since the halogens are much more electronegative than carbon. This means the carbon is delta positive, and so it can be attacked by nucleophiles. And nucleophiles are electron pair donors, and the mechanism for this reaction is nucleophilic substitution. Okay, so the first nucleophile is the hydroxide ion. So looking at this haloalkane, this is 2-bromopropane, and here's the nucleophile. The negative charge is on the oxygen, and also the lone pair is on the oxygen. You draw an arrow from the lone pair to the carbon that has the halogen, and then this bond between the carbon and the halogen breaks, and this reaction forms an alcohol. In this case, it's propantool. And the conditions is an aqueous alkali and reflux. And this is the equation. Okay, so the next nucleophile is the cyanide ion, Cn-. So this haloalkane is chloroethane, and this is the nucleophile. The minus is on the carbon atom, and the lone pair is also on the carbon atom. So as before, the arrow goes from the lone pair onto the carbon, and the carbon-halogen bond breaks. In this case, it forms a nitrile, and this one is propane nitrile. The conditions, ethanolic KCN or NaCN, and also use reflux. Now it must be ethanolic, since if you used aqueous, then the water would act as a nucleophile, and that would produce a different product. And this is the equation. So the last nucleophile is with ammonia. This haloalkane is fluoroethane, and here is ammonia. It hasn't got any charge, but there is a lone pair on the nitrogen. And as before, the arrow from the lone pair to the carbon, and this bond breaks. For this reaction, there is an extra step. It forms this intermediate with a positive charge on the nitrogen here. And one of the bonds between the nitrogen and the hydrogen breaks, and the electrons go onto the nitrogen. And also, there's a second ammonia which accepts this hydrogen, but you don't actually need to draw any of this. But if you want to flex, then you can. And this forms an amine. This one in particular is called ethylamine. And this is the equation. Notice there are 2 ammonia molecules. So the conditions uses excess ethanolic ammonia heated in a sealed container, and it's sealed so any ammonia doesn't escape. And the amine, which is the product, that can also act as a nucleophile, as it has a lone pair on the nitrogen, and this forms different products such as higher order amines. So to stop this, use excess ammonia. There's a greater chance that ammonia is the nucleophile, so there's only one product made. And the second ammonia acts as a base when it accepts protons from the intermediate. But again, you don't need to draw that in the mechanism, only if you want to. So let's look at rates of reaction. with haloalkanes. Down the group, the bond enthalpy of a carbon-halogen bond decreases. That means it gets weaker. And that means substitution can occur faster, so there's a higher rate of reaction. So let's look now at a different mechanism called elimination. We've got 2-bromopropane here, and we've got the hydroxide ion. In elimination, the lone pair goes onto the a hydrogen on a carbon adjacent to the carbon with the halogen. This bond is formed from the hydrogen, and the carbon-halogen bond breaks, and this forms an alkene. In this case, propene. And the conditions are ethanolic and alkali and reflux. Before we used aqueous, and that was nucleophilic substitution, but ethanolic alkali gives us elimination. And this is the equation. It forms an alkene, KBr, and water. And the water comes from this H and this OH minus. And this hydroxide ion acts as a base when it accepts a proton, which is this H. And these two reactions, they occur concurrently, but in each mechanism, the hydroxide ion has a different role. So here it's a base, but in nucleophilic substitution, then it's a nucleophile. And now moving on to ozone. Ozone has the formula O3, and it's formed in the upper atmosphere naturally. How it's formed: UV light causes oxygen to break down into oxygen radicals, and these radicals then react with oxygen to form ozone. And ozone is useful for us because it absorbs UV light, and UV light causes skin cancer. So now let's look at ozone depletion and CFCs. So CFCs are chlorofluorocarbons, and these are compounds containing carbon, chlorine, and fluorine only. So for the initiation reaction, UV light causes carbon-chlorine bonds to break, which forms a chlorine radical and this organic radical here, with the unpaired electron on the carbon. And our propagation, the chlorine radical reacts with ozone, and this forms O2, and the ClO radical with the electron on the oxygen. And this radical then reacts with more ozone for more oxygen and the chlorine radical. And then, it's here this chlorine radical is regenerated, which shows as a catalyst. And this radical can go back here and attack even more ozone molecules. And this is a chain reaction. And overall, if you add these two equations together and then cancel out, then you get this 2 ozone goes to 3 oxygen. So scientists had to do research and peer review, and eventually laws were made banning CFCs in solvents and refrigerants. And now HFCs, which are hydrofluorocarbons, are used because there's no chlorine atoms, so there can't be any chlorine radicals. Okay, so that's it. Please like and subscribe.